I'm going to explain the digital signal processing in somewhat easy way. As the DSP contains a lot of mathematics, obscure mathematical symbols, pages and pages of the equations, this makes the students anxious about the subject of the DSP. So what I will try to do is to minimize the use of the mathematics in explaining the DSP, in explaining the digital signal processing. As although it is not possible to teach the DSP without mathematics. So what I will try to do is to minimize the use of the mathematics and that all that in explaining the digital signal processing. So in today's lecture, I will explain the basics of DSP. What is DSP all about is. So what is the breadth and the depth of DSP? What it has been told that the it is one of the most powerful technology that will shape the science and technology in the 21st century. As we are all aware, another technology is the artificial intelligence. But my topic is DSP in this lecture, so I will go about that. The already revolutionary changes made by the DSP in the various fields. In nutshell, these fields are the communication, medical imaging. It, it saves a number of the lives by making some revolutionary changes in the medical imaging, like CT scans, MRIs, mammographies, and all that. Radar and sonar, this is from the military point of view, and these are the fields in which there is a start of the DSP, use of the DSP. Oil exploration, again, it involves a lot of oil is the base of all the industry, all the you can say the transportation and all that. So it is a very important field. So these are the fields that are shaped already. The DSP had a lot of impact in these fields, in the music entertainment industry. So first of all, what is digital signal processing? What is DSP? So it contains the three terms. One is the digital, another is the signal, the third one is the processing. So I will explain these three terms that contains DSP, that is the digital signal processing. In the very simple form, it is the processing of the signal in the digital form. Okay, but what is signal, what is digital, and what is processing? So start with what is signal. Signal is a function that contains information that can be conveyed, that can be manipulated, or that can be displayed. For example, image is an example of the signal, your audio signal is an example of the signal. And the very simple example that I will take is that temperature is changing with time. You are measuring some temperature with respect to the time, that is your signal. So it is basically a mathematical function in which the temperature depends upon what? The time. And that signal and that function that can be conveyed, it can be communicated, it can be manipulated. It can be manipulated to display it, to control it, something like that. So basically, in a signal, it is your mathematical function in which a one variable will depend upon the another variable. As the temperature depends upon what? The time. As we know, the signal or a function has two variables. One is the independent variable and another is the dependent variable. The dependent variable depends upon the independent variable. In the representation of the signal, The dependent variable is generally taken along the y-axis, and the independent variable is taken along the x-axis. As in the examples that I have taken is temperature changing with the time. Temperature is your dependent variable, whereas the time is your independent variable. Dependent variable is what? This is your actual measurement, that is your temperature. It is also called amplitude, ordinate, or the range. Independent variable is what? When and how these are taken. In this example, temperature is taken with respect to what? The time. These are taken at certain times. That is also known as the domain. As we have, you might have heard about the time domain, frequency domain, and all that. In time domain signals, the measured value, the amplitude varies with respect to the time. Temperature varying with the time is an example that I have taken. Another domain is the frequency domain, in which the signal amplitude varies with the frequency. The signal in the time domain does not convey about the which of the frequencies it contains. To see which of the frequencies are present in that particular signal, what has been done, we take the Fourier transform of that signal. It converts that signal from the time domain into the frequency domain. In frequency domain, the amplitude varies with the frequency. You know which of the frequencies are present in that signal and in which proportion. So another example is spatial domain, in which the signal varies with the distance, in which the amplitude varies with the position. A very good example is the image. In one image, the different pixels have the different intensities. Suppose in a black and white picture, you have the intensity variation from the complete black to the white with the gray shades. So that intensity varies with the position of that particular point in the image. That is called the pixel, your picture element. So we have the time domain signal, we have the frequency domain signal, we have the spatial domain signal. In these three domains, what is changing is the independent variables. In the time domain, in time domain, we have the independent variable as the time. In frequency domain, we have the frequency. In the spatial domain, we have the distance of the position. So second, we come to the digital signal. From signal, we move to the digital signal. As we know, every signal has two variables, independent and dependent variable. So if a signal in which both independent variable and dependent variable are continuous, the signal is called analog signal. In analog signal, we can have any value of the independent variable. It can have any value. It can have 1.2, it can have 2.3, it can have 5.4. There is no restriction on that. Similarly, the dependent variable is also continuous. Like it can have 2.3, 4.5, 7.8, anything like that. Okay, both are continuous. The signal we have is analog. Now, the second type of the signal is discrete, in which the independent variable is discrete. It can have only certain discrete values. It cannot have continuous value. Suppose it can have one, as in the case of the temperature varying the time, we take their values of the temperature at 1 millisecond, 2 milliseconds, 3 milliseconds, not at the 1.1, not at the 1.2. So the independent variable is discrete. But the temperature, the amplitude, it can have continuous values. It can be 30.4 degree centigrade, it can be 40.1 centigrade, So independent variable is discrete, but the dependent variable is continuous. The third signal is the discrete signal, in which the independent variable is discrete as well as the dependent variable is discrete. We can have only certain discrete values of the time and certain discrete values of the amplitude. As in the case of the temperature, it is the, we can have, let it be 30, temperature 31, 32, 33, not 30.1. Is clear? So both independent variable and the dependent variable are discretized in the case of digital signal. In the discrete signal, only independent variable is discretized and the dependent variable is continuous. In analog, both are continuous. Now we know about the signal, we know about the digital signal. And the third thing, that is the processing, digital signal processing. Now we come to the processing. Before that, this is your analog signal. X is varying continuously with respect to the time. T has continuous values, X has continuous values. So the signal is your analog signal. Now, in the discrete signal, we can see along the x-axis we have certain discrete values. Suppose this is 0, this is 1, this is 2, this is 3, and so on. At 0, it has 0 value. At 1, it has 0.6 values. At 2, it has the 1.2 value, something like that. So, it is clear from this that along the x-axis, the independent variable has only discrete values. But along the y-axis, it has the continuous value. It has the 0.6, it has the 1.2, something like that. So when the analog signal is sampled at certain time period, fixed time period, this signal becomes discrete. We have the sampling period after which is signal is sampled. Suppose this is at 0, this is 1 millisecond, this is a 2 milliseconds, this is the 3 milliseconds. So the sampling period will be 1 millisecond. Now, the third type that we have discussed is digital signal, in which both y-axis and the x-axis are discretized. We can have the value of signal at 0, 1, 2, 3, 4. This is discretized. Similarly, along the y-axis, this value is 4, this value is 5, this is 4, this is 3. It is not 4.5. It is not 5.2, something like that. So both the dependent variable as well as the independent variable are discretized. It can have it can have only discrete values along the x-axis as well as the y-axis. We take the analog signal, discretize its x-axis, it becomes discrete signal. Then we discretize its y-axis, its amplitude, it becomes your digital signal. Okay. So in DSP, what we will have is digital signal. So analog to digital conversion, for example, conversion being done with the help of 20 bits at a sampling rate of 1000 samples per second. So sampling period will be 1 upon 1000, that is 1 millisecond. We take the values of the amplitude at an interval of 1 millisecond only. Similarly, the voltage or the amplitude is curtailed at 2 raised to power 12, that is 4096 levels only. It cannot have continuous values. It will have certain levels. How many levels? With the 12 bits of A to D converter, we will have the 4096 levels. As the number of bits increases, the number of the levels increases. Okay, that we will not cover over here. So We take the analog signal, does it sampling, it becomes discrete signal. We take the samples at 1 milliseconds, it becomes a discrete signal. Then its amplitude is discretized and it becomes a digital signal. Now, the third part that is a processing. What is processing? It involves two things: transformation and the manipulation. After the signal is converted into the digital form, the processing involves two things: either it can be transformation or it can be manipulation, or it can be both. So what is transformation? Next point is, what is transformation and what is manipulation? Transformation: for characterization and extracting the information. As I've told you, is for extracting some information, we transform the signal from one domain to the another. As in the case of the time domain signal, we don't know which of the frequencies are present in that. For that, what we have to transform that signal from the time domain into the frequency domain. So how it is done? With the help of the Fourier transform, that we will discuss later on. So in the frequency domain, we know which of the frequencies are present. In time domain, we know how the signal is changing with respect to the time. This is one of the processing, that is the transformation. Second is manipulation, like amplification, filtering, etc. We amplify the signal, we truncate the signal, we does the filtering of that signal to remove the certain frequencies. All that is but your manipulation. So the transformation and manipulation both form your processing. In some cases, transformation is needed. In some cases, your manipulation is needed. In some of your applications, you need both the transformation as well as the manipulation. So the definition of the DSP is its formal definition, that it is the mathematics, it is the algorithm, its techniques to manipulate the signal, to process the signal after these are converted into the digital form. For example, your signal is image. After it is converted into the digital form, its processing can be its enhancement, like the its change in its contrast or the brightness, compression of the signal. All these are what? The processing. The processing done on what? Image as a signal. So basically, in a very simple way, if I have to explain DSP is, we have the analog signal, it is converted into the digital signal, it is given to a computer. Now what next? What has to be done with this digital signal? Here comes the DSP. Whatever you have to do with that signal in computer, in your PC, it will be done with the help of some mathematics, it will be done with the help of some algorithms. That's why DSP involves a lot of the mathematics. You amplify the signal, simply you multiply it by 2, it is amplified by 2. This is the simplest of the examples. You have signal in analog processing. What you need is, for amplification, you need the op amps, you need the resistances and all that. In that, just you need a program of doing what? Multiplying the signal by 2. It is amplified by 2. Is it clear? So all that is mathematics, algorithms that is implemented with the help of some programming in the PC to manipulate the signal, to manipulate the digital signal, is known as the DSP. So whenever DSP is taught, it is taught at the two levels. One is that we will do in these lectures, in the series of lectures, we will learn the general concepts that are applicable to whole of the field, to the field as a whole. In some cases, in the research field, there are some specialized techniques that are applicable in a particular area of the interest. At the bachelor level, at the UG level, this is not needed. What we will do is we will cover the general concepts that are applicable to the DSP as whole, like convolution, filtering, and all that. And we will not go into the specialized techniques that are needed for your particular area of interest, your research area, and like medical imaging. That is one of the example. Speech processing, audio processing, image processing. All these are the some specialized field of the DSP. Some allied areas to study to specialize in DSP, as I've told you, a lot of mathematics. It has the probability, it has the statistics, it may have the decision theory, digital electronics, numeric analysis, and all that. Okay. How much it is needed, it depends upon the depth in which you have to go. For the generalized concept, you may not be need all this. Now, how the DSP is evolution of the DSP evolve, how it evolves. It starts in the 17th century, the processing, not the digital processing. All physical phenomena are explained in the terms of the differential equations. In the start, in the 1950s, when the processing of the signal was done, either analog, it is done with the help of the electronic circuits or the mechanical devices. No computers were there. Before that digital signal processing comes into the scene, the digital systems were used to simulate the signal processing system, only the simulation, before you implement into the analog hardware, resulting in the saving of the engineering and economic resources. How? If that system does not work in the simulation, you don't implement it. So only the system that were successfully simulated were implemented in the hardware. That results in what? Obviously, it it saves your economic, it saves your money, it saves your engineering resources. Then comes with the advent of the computers, when computer becomes cheaper, the systems are directly implemented in the DSP. Some of the One of the reason for that is some sophisticated signal processing algorithms are not available in the analog counterparts. They can be implemented only on the digital system. As we will see the FFT, it is only a thing that is implemented with the help of the DSP. What is the reason for the development of DSP? As I've told you, is the development in the micro technology, lower cost, lower power consumption, discrete type systems, your computers, your PCs. Now, in brief, we will discuss the advantages of DSP over the analog systems, analog processing systems. It can be realized with a general purpose PC or the microprocessor. You have a PC, you convert the signal into the digital, you give it to the PC, and you can do anything on that with the help of your mathematics and algorithm or on a microprocessor. It can simulate analog systems. Before, if some system has to be implemented on the analog part, it can be simulated in the digital, as I've told you, to save the resources. Realize digital transformation that cannot be implemented with the continuous time hardware. There are some transformations, some manipulations that cannot be done in the continuous time hardware. As I told you, one example is the FFT. Operation of the digital circuit do not depend upon the precise value of the digital signals. So the digital circuits are less sensitive to the tolerance of the components and independent of the temperature, aging, etc. What does it mean? As digital signal, digital circuits depend upon only two values, 0, 1, true, false. 0 volt or the 5 volt. So it does not depend upon precisely on that 5 volt. 4.9 suppose can be taken as 1. 0.1 can be taken as a 0. So the precision of the components or the change in the values of the that components with the temperature, with the time, with the aging, it is not dependent on that. That is one of the major advantages of the DSP. Very highly sophisticated, dedicated, you can say, complex digital signal processing systems can be integrated on a single chip. You have PC. You can use it for a number of signals. It has a very powerful processing capabilities so that you can process a number of the signals with the help of one machine, with one PC. So thus reducing the cost of the processing per signal. You time share your machine, you time share your PC among a number of signals, and the processing cost becomes cheaper. Analog processing cannot be done for the low frequency signals, whereas the DSP can be used for that. We will see why. As we know, the impedance is 2 pi FL, whereas in the capacitive it is 1 upon 2 pi FC. See, for low frequency signals, F is very low. F is very low means XL is very low. It is almost short circuited. Similarly, as in the case of XC, F is very small, X is very large. Almost it is open circuit. So as to make it a reasonable value, we have to make L very large. So XL is not very small. Similarly, in this you have to make C very large so as to make XC some reasonable value. So we need very large inductors and large capacitors that may not be feasible, practically feasible, or it may be very costly. So in low frequency signals, what we use is DSP. The last one, this is the most important advantage of the DSP. You have to change the operation of the DSP, you simply change the program. You are amplifying by 2, you multiply it by 2. You want to amplify it by 4, what you have to change is just to change the value of the 2 by 4 in the program. Whereas in the analog processing, what you have to do is you have to do the redesign the hardware. You have to change the values of the resistances. Redesigning, that is costly, that is time consuming. But in your DSP, just what you have to do is you change the program, your processing is changed. As I have given the example, you want to amplify by 4 instead of 2. Just you have to rewrite the program and change the 2 by 4, it is amplified by 4. That is the main advantage of the DSP. Easy storage of digital data. As you all of know, it can be stored in pen drives, it can be stored in hard drives, anything that is very easy. And that data is transportable. You can take it to some other location for the processing of that. And it can be processed offline. As the data is stored with you, you can do it at any time. As everything which has advantages is bound to have some limitations also. So as the DSP. Complexity of the system increases because you have to, most of the signals in the real time are analog. So first of all, you have to convert it into the digital. After processing, again, it has to be converted into the analog for further use. As the complexity increases, reliability decreases, chances of failure, and the cost can be increased. Limited range of frequencies available for the processing, depending upon your circuit, hold circuit, and A to D converters. Digital systems are made of active components, so more power consumption and less reliability. So these were the most of the advantages and with very limited number of the limitations. So next we will see the applications of DSP. Space, space photography enhancement, data compression, medical. That is a very important applications in the medical, diagnostic imaging, ECG analysis. You can do the analysis using the computer, medical image storage, retrieval analysis. So improvement in all these things can save a number of lives. The data taken in the space is very important and costly. So again, DSP comes into come into picture in there. In commercial applications, image and sound compression, as in the music industry, you can say it can create some special effects in the movies. These are the commercial applications. Number of it has in that communication, voice and data compression, echo reduction, signal multiplexing, filtering. In military, you have the radar, sonar, and secure communication needed for the military purposes. In all these things, your DSP comes into the point. We have the industrial applications, oil exploration, process monitoring and control, as in the case of instrumentation and control, computer aided design, data acquisition, spectral analysis in the scientific research, simulation and modeling. Number of the application. As I've told you, you need no to go into the depth of that. We will learn the general concepts that can be applicable in any of these applications. If you have some research area, you have some particular area of interest, then you have to learn some in-depth algorithms, in-depth techniques that are applicable to a particular area.